Hey everyone, welcome back. So the paper we are going to be discussing today is called AlmoTrace by Alan AI. Imagine a language model is powering an agent. The agent takes a decision which causes billions of dollars of loss in the business. Questions are asked, but no one has any answer. As large language models are used more often, especially in important situations, it is crucial to understand why they generate a specific response. Existing methods struggle to trace language model behavior back to training data due to massive scale and computational demands. AlmoTrace is introduced as the first system designed to trace language model outputs back to their complete multi-trillion token training data in real time. It works by finding and displaying exact verbatim matches between parts of an LLM's generated text and the documents within its training dataset. The key to AlmoTrace's speed is efficiently finding exact text matches within the vast training data. This is achieved by pre-processing the training data using a technique based on suffix arrays. Imagine a very short text, banana. The suffixes are banana, anana, nana, and so on. You get the point. A suffix array stores the starting positions of these suffixes after they are sorted alphabetically. Thus, the suffix array of this word would be 531042. We will see how this is used in a moment later in the video. So there are 5 key steps to tracing the output of a language model. First is finding maximal matching spans, which identify all text segments in the language model output that exist verbatim in the training data. These spans must also be maximal, meaning they aren't part of a longer matching span, and self-contained, which means generally not crossing sentence boundaries like periods or new lines. To avoid overwhelming the user, the system filters the found spans. It keeps only a small number proportional to the output length of the most interesting spans. Interesting is defined by the lowest span unigram probability, a measure combining length and uniqueness. Spans that are longer and contain less common words have lower probabilities and are preferred. Thirdly, retrieving enclosing documents. For each selected span, the system retrieves up to 10 document snippets from the training data where the exact span occurs. If a span occurs more than 10 times, only a random sample of 10 is kept. Next, merging of spans and documents. Overlapping spans highlighted in the language model output are merged into single larger highlighted regions. Similarly, if multiple retreated snippets come from the same original training document, they are grouped together. And finally, re-ranking and coloring the documents. The retrieved documents are ranked based on the relevance to the user's prompt and the language model's response using a BM25 scoring algorithm. Documents are then assigned a relevance level, high, medium, and low, and color-coded accordingly. The actual algorithm leverages something called Infinagram. Instead of checking every possible subspan of the language model output, the algorithm cleverly works with suffixes. For each starting position in the language output, it considers the suffix starting there. Example, if the output is ABCDE, it considers ABCDE, BCDE, CDE, etc. Now let's take a toy example of a sentence such as cats are cute. So the model output, cats are cute. Let's check if this exact phrase appears in our training corpus. Let's assume that we search our training data using Infinagram, but the exact phrase isn't found. Instead, Infinagram returns the lexicographically closest matches. Cats are and cats are fluffy. Looking at our matches, we can calculate the longest common prefix. When comparing with cats are, the LCP is 2 tokens. Similarly, the cats are fluffy, the LCP is also 2 tokens. Therefore, the longest prefix of cats are cute is actually cats are. This approach helps us identify which parts of model outputs are directly present in training data versus which are novel combinations. The algorithm as well is pretty simple. The process starts by examining every possible starting position in the model's output. For each position, we extract a suffix, all tokens from that position to the end. We then query the Infinagram index to find the longest prefix of this suffix that exists in the training data. If the exact suffix isn't found, we look at the closest lexicographic neighbors and calculate the longest common prefix with each of that. This search happens in parallel across all starting positions, giving us many overlapping spans where content matches the training data. The final step filters these to keep only maximal spans, which means those not contained within larger matches. The result is a precise mapping of which segments in the model's output directly correspond to memorized training versus which are novel generations. The paper shows how AlmoTrace can be applied to three very specific use cases. Firstly, fact checking. If a language model makes a factual claim, example, the Space Needle was built for, let's say, the 1962 World Fair, AlmoTrace can highlight this span if it appears verbatim in the training data. Users can then view the source documents and potentially their original URLs to assess the reliability of the information. Next is tracing creative expressions. Language models sometimes generate text that seems novel or creative. AlmoTrace can reveal if seemingly unique phrases or sentences were actually present in the training data or if the language model is simply faking. And finally, there's something called tracing math capabilities. It can help understand how language models perform calculations or solve math problems. If a language model solves a math problem and shows its steps, AlmoTrace might find the exact calculation, example, the binomial coefficient calculation for a particular binomial. Does it appear verbatim in the training data? AlmoTrace can figure that out. And that was all for today's paper. If you like this video, you know the drill. Like, share, and subscribe. And I will see you next time.